All right, so how does a magnetic field affect a moving charge? If we have a charged particle that is moving through a magnetic field, in other words, we've got an electron, we've already got a magnetic field established, and an electron is actually moving through that magnetic field. What's going to happen? The big thing you need to remember is the right-hand rule. This is another version of the right-hand rule. In this particular chapter, we're going to have 3 versions of the right-hand rule. Okay? A charged particle traveling it experiences a magnetic force. This word right here is important. Perpendicular to the field. Now, this right-hand rule is this. Okay? Using your right hand, you've got 3 dimensions. This is what we call a cross product. Okay? The cross product between these 2 fingers that are in the same plane produces the magnetic force that's this way. Okay? In other words, if you've got a B field, which direction is this B field going? Into the page, isn't it? So if you have a magnetic field going into the page, let's see if we can do this. Let's see. Into the page, this is my finger here. And these fingers are the direction of the velocity, okay? Then this is the direction of the force on the object, the magnetic force on the object. And remember, the magnetic force is what's going to move it up or down or side to side or whatever. So what you have to do is 2 of the fingers, and it doesn't matter which fingers you use, because this is 3-dimensional, isn't it? And think of it as X, Y, and Z. So if X is the direction into the page, and I'll try to do this, if this guy is into the page, this guy is going which way? Here we go. We can do it that way. Into the page. This finger right here is the what?
This way?
Yep. If you've got one finger going into the page, one finger going, look at it. One finger's going into the page, that is the magnetic field, isn't it? This finger right here is the velocity, the direction of the velocity. That means this finger is the force. My thumb is the force. That's what we're talking about. You will see yourself doing this with your hand trying to get it to work, but it's true. This way, if the B field is going into the page, the velocity is going this way, then the magnetic force is going down. Okay, there is a magnetic force being created by that guy down. So you've got 3 dimensions. I want you to think about it. If you were looking in one dimension, you've got one dimension going into the page, one going this way. What's left? Z, the other dimension, isn't it? The other place? So if you've got one going in, this crossed by this gives you a result of the magnetic force, which is F sub B, going down. Okay? That is your B field. So if B is going in, velocity is going this way. So B cross V. That's what we're talking about here. In reality, the math form of this would be B crossed with V gives you the magnetic force. Okay? You okay, Ruby? Okay, gives us the magnetic force. Now, magnetic force, of course, is this guy right here, F sub B. This is my magnetic force. Oh, please tell me this didn't just... Can you tell it's a Monday? I can tell it's a Monday. Give me a second here. Gonna have to let the pencil charge for a minute. It's a magnetic force, okay? Take a look down at example A. It says specify the direction. We've already talked about this, and I'll put some extra stuff up here, but let's look at this one. My pencil is charging, and see if we can't figure out what direction each one of them is going, where F sub B is going. Okay? So look at A and figure out what direction the magnetic force is going. Coming out of the page, coming out of the page and going which way? That way, right? Out of the page and this way. Which way is my thumb pointing? Up. So guess which way the magnetic force is? Up. Which means is this particle, I want you to think about what's happening here. If this particle is going through this magnetic field and you've got a magnetic force pushing up on it, what's the path of this electron going to look like? Yeah, it's going to curve up, isn't it? It's going to be pushed up.
What's the other thing we did that they did the same way?
We have 3 different, in physics 1, angular momentum. Torque and angular momentum are both. Torque is the right-hand rule, it's that same right-hand rule.
I think
If you've got a force in a direction, the torque tells you this tells you the direction. So if I apply a force in this direction, then this is where the torque's going. This is why right-hand rule works. Or this is why righty-tighty works. And lefty-loosey works. Okay? Look at B. See if you can figure out B. Which direction is it going? Sometimes it's easier to do it with your thumb, too. One finger's going in, the other finger's going down. So which direction is the force is going to the left? So B is to the left. Is it to the left? Hang on. Oh, is it into the page? Yeah, into the page, down. Yeah. Into the page. And down. Oh, but it's, look at the charge on it. Oh, what does that do? Into the page and down puts the force to the left normally, but that's for an electron. So now what happens if it's a proton instead? It flips it the other direction. You seeing that, Manny?
Yes.
So what is the answer for B?
Really should be to the right.
Really should be to the right. So you've got to consider that too. So now look at C, because now you've got to look at not only what's happening here, but you have to figure it out, and then you have to look at the sign and see if it really is going that direction or the opposite. So figure out what direction C is going. So out of the page in this way puts it going which way?
Down. Yeah, down.
Is it out of the page or into the page?
It's
Out of the page. So my finger's going this way, it's going this way, so up would normally be the case, right?
Yep.
But it's
positive.
so it's down. All right, what about D?
Out of the page.
So velocity is going what? B field's going down, right? Velocity's going this way. Velocity, B field. Why'd you say out of the page, Manny?
Out of the page because the field's going down, the velocity of the charge is going to the
Yeah.
right. So that makes a plane.
Pointer
and then-
finger has to go in the direction of the B field, doesn't it?
Mhm.
This finger goes in the direction of the velocity. So this way and this way, so it's pointing out, right? Okay. Let's double check this one. Out of the page this way, should be going up, but it's this so it's actually going down, okay? So now what about E?
Going into the page.
Velocity is,
Yeah.
Oh my goodness.
this way.
Yep.
No,
To the page.
the pointer fingers of velocity.
Whoa.
So,
And
Well, which is which?
I got into the page for.
if the thumb point is the direction of the field.
Is this hard to do? Is this really hard for y'all to do with the three fingers?
Not really.
Try it this way. You can also do it this way. If you make your thumb the velocity and your fingers B, then your palm is the direction of the force. Does that feel better? V, B, direction of the force. Maybe that'll make it easier.
I mean, the finger.
So V is your thumb.
Word. It's just like you orient your hand.
Yep.
Differently than I think I'm holding it, and then like it flips.
Okay. So V, yeah. See, if V is here, B is here, then the force is going up, right?
But it's.
But this is positive, so it's going down. All right, so for this guy, V is my thumb. Jeez, it's so hard to do here with this screen. V is my thumb. Fingers are what, down? So V is my thumb, fingers are pointing down, so it should be going what? Into the page, correct? Okay,
Okay, no, I got it.
V is into the page. Oh shoot, did I just do that backwards for y'all? If the moving charge is negative, use the left-hand rule. Right-hand rule is for the positive charge. So C is up. So A, I've just taught you this backwards. God, I hate, it's Monday. It is freaking Monday. So this, the right-hand rule is for a positive charge, and then you flip it if it's a negative charge.
Okay. Yeah, that makes sense. I don't
Yeah.
have to do all that. Just-
Mm-hmm. So this guy should be going up, correct? So A,
Everything's just backwards.
velocity is what? Velocity is this way. Field's coming out. It would normally be down, but it's negative, so it's up. And since it's all backwards, if you want, you can use your right hand for the positive charges and your left hand for the negative charges, so you don't have to contort your hand. So positive charges.
So the left. Are we doing the three fingers? The thumb points the direction of the field. The index is the velocity, and then this is the direction.
Yeah.
So
So let's make sure that works. So for negative, what? What do we have? Down and this way. So which direction is the force going? Into the page. Out of the page. What are we talking? I just prefer to use the same hand for everything and then just flip the direction if it's an electron. Okay? And it's easier, V, do you know how I remember this is, if I use this rule with the palm, it's rather than having to contort my fingers. If you use this rule for your V, you notice there's a V right here? V, B, F. So V, B, F, coming out of your palm. So let's look at D. If we had V this way, B would be what? This way? Yes? B is this way. B is down. F is going which way? Into the board, but it's negative, so what?
goes
Out the board. So this one's out of the page. So now let's look at E. It's It takes practice, doesn't it? Okay, so E, here we go. Let's try this one. This one's straight up, whatever it says, because it's positive, right? V is what? V is down. V is this way. So what's happening?
Coming out.
Out of the page. Okay, now we got this. It's almost easier than the three fingers because my fingers start to hurt with that. And you have to remember what's what? V, B, F. So find F, which way it's going. What's the problem with F?
You got a charge moving in the opposite direction of that.
You got a charge moving parallel. In every one of these other cases, for us to use this rule, they had to be 90 degrees from each other, didn't they?
Mm-hmm.
Perpendicular? So what about F? It's just moving through the field. There is no force generated because the vectors, the V and B, are not perpendicular to each other. V and B have to be perpendicular to each other. Okay, so let's wrap this up with this, okay? Let's look at this and see what we've got. Let's make some final things. What do we know? We know that F of B is, the actual formula right here is F of B equals the charge strength, makes sense, doesn't it? And then V cross B, okay? Now, since it is V cross B, what we do is write it down as QVB sine theta. Now, what is theta? It is the angle between the velocity and the magnetic field. So it doesn't have to be exactly perpendicular, but do you understand why this means that one down example F is wrong? What is the sign of 0? 0. So if they're parallel to each other, that rule makes sense, doesn't it? Now, what if it's not exactly perpendicular to each other, but it's somewhere between perpendicular and parallel?
Gotta take that into account.
Then it only gets the part of the B field that is actually perpendicular to the velocity. Okay, that's where the sign of the angle comes in. So if it's moving at a 30-degree angle through, it would be QVB sine 30 degrees. Okay? So it gets part of it, but not all of it. So this, if you remember, is V. This is B, and out becomes F sub B. And this is for a proton. So for a positive charge, right? How does it work for a negative charge?
Same way, usually flip.
Yep, just flip.
Just use your left hand.
Flip the direction of F sub B for the right-hand rule, or use your left hand. Okay? So, are we good with these? So we knew this one was what? What was A? What did A end up being? I think it was
Down.
up. Remember we said it, we went back through and said it's a negative charge, so
Yeah.
out of page, to the right,
Yeah, I got down.
yeah, and then it's negative, so you have to flip it.
No, that it was up originally because I used it.
Negative. Out of page this way. Whoa, hold on.
It's out of page. Hold up.
Out of page, because it's dots. Out of the page, this way, should be down, but it's negative, so it flips it. Manny,
Oh, it is up. It is up. Yeah. It is.
Manny. Don't contort so hard. Look. Out of page, to the right, but negative, so it flips up. It's hard. You start, yeah, exactly.
But what's the transition?
Uh-huh. All right. So this one was ended up being to the right. This one was up. This was out of page. Hold on. Out of page. This way. Out of page. To the right. Up. It's up. Out of page. To the left. Yeah. C. E was out of the page. Yep. And F was none. Okay? So now, can the magnetic force change a charged particle's speed?
Yes.
No.
No, of course not.
Can change its what?
Velocity.
Direction.
Direction.
It's pushing on it up or it's pushing on it down. It can't, the only way it can change the speed, guys, think about it. The only way the force can change the speed is if it's pushing directly behind it or at an angle at it, but it's never going to because the cross product says if the speed is this way, this is 90 degrees to it. It can only push it up or push it down. Think about that.
Okay.
It's got to accelerate in the same direction as the velocity. The force is never going to be in the same direction as the velocity. If this is the velocity, this is the force.
Mm-hmm.
This will never be in the same direction as this.
Right.
So it can never speed it up or slow it down. But if you've got a velocity going this way and you've got a force going this way, it's going to push it or, yeah. So the answer is no. F sub B is always what? Perpendicular to the velocity, right? Okay. So we have a proton. You're going to see these three-dimensional graphs here. We've got a proton moving at 5 times 10 to the 6 meters along the positive x-axis. So this is our velocity along the positive x-axis right here. It enters a region where there's a magnetic field of 2.5 Teslas directed at an angle of 30 degrees with the x. Find the initial magnitude and direction of the magnetic force on the proton. We need the direction. So, V and B. V and B are what? V is this thumb, right? So it would be V and B is somewhere in the Y direction. So which direction is the force going? Up. Which is in the positive Z direction. So we know the direction already is positive Z. Okay, now we've got to find the magnitude. Magnitude's just the formula. F sub B is Q V B sine theta, isn't it? Well, what is the charge of a proton? This is on your formula sheet, 1.6 times 10 to the negative 19th, isn't it, coulombs? V, velocity, is 5 times 10 to the 6th. B is 2.5 Teslas, and then the sine of 30 degrees. And it's just a math problem at that point.
So Q is that number for the proton?
Q is the charge,
The charge?
isn't it? Think back to your electrostatics. It's the charge on a proton. Electron and proton have the same charge, don't they? 1.6 times 10 to the negative 19th. So run that through your calculator and let's see what we get. Got 1 times 10 to the negative 12. And what would the units be on that? It's not a trick question.
8.72.
I got 1.1 times 10 to the negative 12.
So I got.
How'd you put it in there, Ruben? And double check to make sure you're in degrees also, not radians.
Probably radians.
What are the units? It's force, guys. What are the units for force?
Newtons.
Thank you. You get so used to not thinking about physics 1 stuff, you forget some of the fundamentals, like the units for force are newtons. Okay? So now, did you figure out what you did wrong? Okay.
Oh, there you go.
Mm-hmm. Motion in a circle. So what happens if the charge is traveling in a uniform magnetic field, experiences a constant force perpendicular to its motion? Because that's what's happening, isn't it? Where else do we see a force that's perpendicular to the motion? What type of movement in physics 1 did we see where the force was always perpendicular to the movement? What's happening? It's always pushing it, pushing it, pushing it, pushing it, pushing it, pushing it. Think centripetal force. Isn't centripetal force always perpendicular to the motion? Where do we see centripetal force?
On that turn.
On a turn when something's moving in a what? In a circle. So if we have motion, if we have this velocity here, in other words, we have this electron or proton moving through this magnetic field that's always perpendicular to it, it's going to end up traveling. We already said it's going to move it up or move it this way, isn't it? Well, it's going to continue to affect it. And then finally, when it's moving this way, when it's curved enough to move this way.
Miss Duffy?
Yes?
Can you send Ruben Saavedra to the main office, please?
Sure.
Thank you.
When it's moving this way, now it's being pushed this way. So now you've got it moving and it's eventually going to move, just keep on affecting that B field's going to keep on pushing at it. At cross product, it's going to end up going in a circle.
The electron?
Yeah. The electron will end up going in a circle.
Would that just make another magnetic field?
Or the proton. Aha. All right, so what do we need to know here is when the force is always perpendicular, and the velocity, the direction's always changing, it's traveling in circular motion, which means this. F sub B equals F centripetal, doesn't it? Which means this. B Q V equals mv squared over r, doesn't it? We can get rid of one of the v's, can we not? One of the v's goes away, so what we get is bq equals mv over r. Now, I want you to read what this says, the next chunk says. What we're going to end up with is this. This is what the path is going to look like. As V gets over here, by the time V is over here, going this way, what we're getting is it's going in this circular path, okay? Where the force magnetic does that, towards the center of the circle. It changes. Think about why it's constantly changing direction.
Because it's perpendicular to one time.
Yeah, well, and the force, it's creating this force that's pushing it this way. So as the thing changes direction, then you're changing the angle. You're basically changing your F cross B. Your V is changing slightly. The direction of V is changing. So if the direction of V is changing, then the direction of the force is changing, putting it around. Until it's up here, and now it's going it's going this way down instead of up, because the velocity has changed directions from going to the right to going to the left. And then it's this way. See what I'm saying? Now, what happens if the initial velocity is not perpendicular to the field? If it is not perpendicular, perfectly perpendicular field, if it's at an angle, not only is it moving in a circle, but there's an extra component that's in the other direction, isn't there? That's moving it either up or down at the same time. So you've got it going this way, and now it's moving either up or down.
So like the shape of a spring.
Helix. Yeah, we call that a helix. It is a helical path. Okay? So it's moving in this circular path this way, but it's also got a component that's moving it that way as well, or the other way. So you've got a component of the velocity moving this way, but you also have the component, think of it as the x and the y, you've got a component of the velocity moving it the other way. So it's either making it helix up if it's in the positive y direction, or it's helixing down if it's in the other direction. All right? So now, let's look at an example here. Charged particle of mass m and q moves in a magnetic field with a flux density of b in circular motion. Derive an expression for the frequency of its circular motion. So what do we know? If it's moving in a circular motion, we know F sub B is equal to F sub C, don't we?
Yep.
Okay. So we know that BQV equals MV squared over R. Yes? So that we know V, if we solve for V, let's go ahead and solve for V. We get V is equal to B, let's see, that goes away, this goes away, so we have V. BQR over M. Now why do I want V? Because we want the frequency of its circular motion. Frequency, if you remember, is 1 over the period, correct?
Right.
And the period is 2 pi r.
It's gonna be 2 pi, basically.
So it's 1 over 2 pi r. So now what? Oh, it's not 1, it's V. It's V over 2 pi r. So now we just plug V in. So the frequency is now going to be V, which is BQR over M over 2 pi r. We have R in the top and R in the bottom. So we have BQ left in the top and 2 pi M in the bottom. So there's my frequency. All right. Now we're going to get to something that's a real serious thing that when you get into, if you're thinking about going into any sort of engineering, especially electrical, this is a deal. I want you to think what's happening here. We have a charge moving through a magnetic field. Now, what is the magnetic field most likely created from? Current, right?
Yeah.
So if we have a charge moving through a magnetic field that's created by a current, that magnetic field, that current has also got an E field, doesn't it? So now what happens if we have the combination of both the E field and the magnetic field at the same time? We call this a Lorentz force. It's the total force, okay? So this is big F, total force, which is your Lorentz force, is going to be the force through the E field plus the force of the magnetic field? This is a biggie. E field is QE. Magnetic field is QV cross B, isn't it? But that is the Lorentz force. So we've got to consider both, because it's not just being, it is not just being influenced by the magnetic field, it's also being influenced by the electric field. That's basically what the Lorentz force is telling you. It's being influenced by both fields there. Both fields are producing a force on the particle. So let's look at example E. We've got a potential difference between two plates. The potential difference is 850. That means this is the voltage, doesn't it? Voltage is equal to 850. That's what potential difference is. We've got a magnetic field of 0.76 Tesla into the page between the plates. The plates are 0.8 meters apart, and the particle passes undeflected between the plates. And it says, okay, so what's the sign on the charge of the particle? Can the sign of the charge of the particle be determined? And if it can, the answer is yes, it can be determined, because we know it's not deflected. If it's not deflected, what does that mean? We've got one field, the magnetic field is going to deflect it, isn't it? Which means the electric field must be going in the other direction of it, doesn't it? And if it's pushing in the other direction, then we know which direction what charge is on that particle, don't we? So we've got a velocity going where? Into the page, right? Velocity is this way, into the page this way. So which direction is it deflecting? Up? Right? Say yes or no. Up?
Hold on, what?
We don't know the charge on the particle, so we're going to assume for now it's positive. Okay? If it's going into the page and the velocity is this way, we know the force, the B force, is magnetic force is up, correct?
Right.
Okay. So if the magnetic force is up, then the electric force must be, so we're going to start with for A. If it is positive, then we know F sub B is up. So F sub E must be down, correct? Is F sub E down? Can we tell what direction the magnetic force is in?
It would have to be down since you're using the right-hand rule, and since you're using the right-hand rule, it would have to be positive.
Here's the problem. If it's negative, then what? F sub B would be what? Down, so
It would also work if we were that way.
exactly. So can we tell what the sign on the particle is?
Apparently not.
No, we can't tell that. All we can tell is what would happen if they were positive. Now, for part B, what's the speed of the particle? We can tell that because it's undeflected. Undeflected tells us simply that F sub B is equal to F sub E. So we don't have to know the charge on the particle, or we don't have to know the sign of the particle because we know the charge on the particle, don't we?
We do.
Whether it's an electron or a proton, it's still 1.9 times 10 to the negative,
1.6 times
1.6 times 10 to the negative 19, don't we?
Yes.
So it doesn't matter. So we just say, okay, this is going to be what? QVB. And this is going to be QE. Matter of fact, we don't even need Q. We just need to know B and E.
Okay.
So it's going to be E divided by B, isn't it?
Oh, okay, I see how we do it. So then an E is equal to
The
V over
potential
R.
difference, well, yeah,
So that would be
just V.
V equals voltage V over R.
So this would be V over B. Mm-hmm.
No, you need the R as well.
Okay.
So it would be V over RB. Or voltage V
Mm-hmm.
over RB.
Yep. What is R gonna be?
That would be 0.8, so
Mm-hmm.
50 over 0.8 times 0.76.
Times 0.8.
That would be,
About 1,400?
yeah.
Yep. Meters per second. So notice that R is actually the D between the plates. So you knew that.
Mhm. Oh.
All right.
That's good.
Positively charged particle of mass M equals 2 milligram, or 2 mg, excuse me. Should M? What would M be?
Are you sure it's not just milligrams? Because it could just be that.
It's awfully big.
Two milligrams is awfully big.
For a positively charged particle. I would think it would be more like nanograms. It's got to be small. Let's make it nanograms.
Sure. Maybe like something cancels out and it works out perfectly or something.
I don't know. I'm going to make it nanograms because that seems awfully big. Milligrams would be really, really, really fat particle. You'd be able to see it. That's not cool. Charge of microcoulombs accelerated from rest reaches a speed of 2 times 10 to the 6th. Ooh, it's humming along. When it enters region 1, which has a constant speed, after which it has a constant speed. If it has a constant speed, what does that mean?
That means there's all the forces acting on it are
Cancel out.
they cancel out.
Yeah, net force. That whole constant speed thing means that the net force equals 0, doesn't it? That tells us it's undeflected. And now it nicely tells us that in the next line. It travels undeflected in region 1 and then enters region 2, where it travels in a semicircle. By the time it gets out to the end of region 2, because it hits the magnetic field, but it no longer has an electric field, right?
Uh-huh.
So now it's going to move it's going to be deflected. And it says, calculate the radius of the circular path the object travels in and specify which way the particle curves. Does it curve up? Does it curve down? Which way does it curve? In other words, is it going to move up or is it going to move down? We don't know. Which one do we? So we got to figure out what's going to happen here. Okay? So let's do the math and let's look at part A. Calculate the magnitude, not magnetic. The magnitude of the potential difference. So in other words, we want to find V. Correct?
Right.
All right. So we got to find V. Well, potential difference is just work done, isn't it? Think about it. Potential difference, this is going to be the same as saying what's the work done, which is the change in kinetic energy, isn't it?
Well, there's no
Yes.
change in it,
There's a change in the kinetic energy.
but it's not. It's like at a constant velocity, right? So there should be no change.
From rest and reaches the speed of when it enters region 1.
Oh, okay, I see.
Okay? Once it's in region 1, it travels at a constant speed.
Okay.
So we need to know how much potential it has when it gets to region 1. All right? Because we're going to need that, aren't we? So, potential difference is equal to K final minus K initial. K initial was 0 because it was started from rest, correct?
Right.
All right. So this is VQ. That would be work. Excuse me, not just V.
Yeah,
VQ.
because I was looking at my paper, it was like delta UE. and
Yeah.
QV. I was
Delta UE is QV. So now what? This is going to be 1/2. Divide both sides by Q. So we end up with mv squared over 2Q. So let's figure it out. Mass is 2 times 10 to the negative what? Nanogram is what, 12?
I have no idea.
I think it is. Micro is 6, pico is 9, nano is 12.
Okay.
10 to the negative 12 kilograms, or grams. Or maybe I've got that backwards. God,
You wanna check?
let me remember. Let me remember what the, yeah. I think it even tells you on yours
Oh, actually, hold up. Just check right here.
what the different ones are.
Nano is to the -9.
Negative 9, but I want to put it in kilograms anyway, so 10 to the negative 12 kilograms.
So picograms?
Pico would be to the negative 12?
Yeah, that's what it says.
Okay, so I got nano and pico switched.
Okay.
At the last second, I thought, wait a minute.
Pico
Is that
sounds
right?
a lot smaller too.
Yeah.
Anyways.
All right, so it's 2 times 10 to the negative 12 kilograms. Everyone knows where that came from.
Yes.
2 times 10 to the negative 9 grams, which becomes 10 to the negative 12 kilograms, which we need in kilograms anyway. All right, now, velocity. 2 times 10 to the 6 squared, correct? And the charge is what?
That worked a little too
4
quick.
microcoulombs.
But
4 times 10 to the negative 6.
I did it right now. It worked a little too quick.
So we got 2, 2, and 4 goes away. And 2 squared 4, oh yeah, it's going to be 1 times 10 to the 6th.
No, it's just 1. Because when you multiply the, and you're missing the 1/2. This is 1/2 mv.
Oh yeah. Well, this and this go away because 2 squared is 4. This 4 goes away. 2 and 2 go away. 10 to the negative 12. 10 to the positive 12. So it is 1. You're right. It is 1, isn't it? It's just 1 what?
Just 1 volt.
1 volt. Potential difference is 1 volt.
Let's never get that.
I know. Magnitude of the electric field. Magnitude of the electric field we can find F sub E because we know that's equal to F sub B, isn't it? Because it's undeflected. So that is what? Q E equals QVB, correct? So the Q goes away, so E, magnitude of the electric field, is just going to be V times B. So V is what? The velocity is 2 times 10 to the 6th times 0.5. So it's 1 times 10 to the 6th. What? Newtons per coulomb. Think about how I know that so fast. What is force? Newtons. We're going to divide it, but we divided it out by what? Coulombs, because the charge. so newtons per coulomb. And now C. The radius of the circular path, what do we know? We know on the outside there's only what? Magnetic field, right? Well, in a magnetic field, we know it's going to move in a circle, don't we? So F sub B equals F sub centripetal, don't we?
Right.
So this is going to be what? QVB equals MV squared over R. And we're actually looking for R, aren't we?
Okay.
So we got this and this one away. So R comes to this side, and we end up with MV over QB.
So that would be
2 times 10 to the negative 12. Velocity was what?
was
2 times 10 to the 6th. Q is, what did we say?
It was
4 times 10 to the negative 6. And 0.5. Ah, so we get 2. Yeah, really we get 2 meters. It's a 2 meter deflection. All right, you guys need to do, that was the end of 5.2. So you need to do 5.2 exercises, all right?
5
And the other 2 sets of topic questions, okay? 5.2 and the 2 sets of topic questions are your down. So your homework, so I can post this, 5.2 exercises, and by all right.